Alright, guys, welcome to the AI workshop number 3 on time series analysis. I guess we'll wait for a couple of minutes. It's supposed to start at 6:30, so we are gonna start on at that time. So, how are you guys doing during this particular situation for COVID-19? We are gonna do something related to that, but before that, let's just go ahead and get started as to how you guys are coping up around this. All right. So I guess the live chat is also up and running. People are there. So just a couple of minutes. I think 6:30 is when we want to start. All right, so let's go ahead and get started. Uh, First things first, I think we have sent out the board applications for the club, and that should be there on the people's email. So, any of you guys interested in those positions, please go ahead and apply because we are actively looking for people. So that it would be great, and that's how the club would actually grow. So please go ahead and do that if you haven't done, and if you have done it, all the best with the next few steps. All right, so let's go ahead and get started with this particular workshop. So we had sent out a teaser video if you guys had seen that earlier, and we said that we are gonna do uh, a basic introduction as well as the norms and methods which we use in doing a time series analysis, and that's how we are gonna look at this particular workshop. But on a higher level, there are many more things which you can do with respect to methods and approaches in time series analysis. And that would be difficult to cover in an hour, and this workshop wouldn't be able to accommodate all that. So having said that, let's go ahead and get started. So we have on our agenda is what exactly is a time series. So people who have never heard of that or have never done any kind of analysis on it, uh, we will definitely let you know. And then we are going to look at few other properties of time series, what are those and what are the different models. So we have a statistical model which is known as the autoregressive integrated moving average, ARIMA models. We'll come to that, and as well as the deep learning models. We will also see how to forecast this data and to check if and how to evaluate our models along with the pros and cons which are there. And finally, we would be looking at implementing two of the time series models which we have, and I think the GitHub links will be up along with the video, I think, post this. If it is not, just let me know. I'll post that on the chat window. So we are going to use we are going to evaluate two of the data sets. One is for the air quality and the other one is the COVID-19 data set. I think COVID-19 data set has become a very used data set now on Kaggle. I think few of them are there. Air quality UCI is a data set which is available on the UCI ML website. So we have a repository for a lot of data sets which are used in research, and we have and one of them for air quality, and which has been used for time series a lot, and we are going to evaluate that particular data set. So let's get started with what is a time series. So time series is anything which has data points which are indexed in a time order, right? So you have, let's say, time order which is 1, 2, 3, 4, 5, and at each interval of time you have some time. You have some data point. So it's a it's in very loose terms, it's a equation where you have y is equal to mx plus c, but it doesn't always have to be linear. It goes into a non-linear domain. So data points in such are ordered in such a way that they are ordered in a equal interval of time. So that is how you define a time series. And when we do a time series analysis, we have to look at the fact that how the output or how the data is auto correlated with itself. Because if it is not auto correlated, then you are looking more towards a general machine learning problem where you have the dependent variables other than the independent variable. Here in time series, you have the independent variable, which is the data you're looking at, look as well as itself being the dependent variable. So you have y of x, which is dependent on the previous values of y of x. So in a way, that is how it is. So there are certain statistical methods which are useful for like basically a time series analysis is a statistical method to derive different intuitions about the data. So it's not only about forecasting, you also want to know how the data changes through time, right? Like what is the mean, what is the like how much is the data varying after certain intervals of time. Uh, let's say you have certain things like Black Friday and things like that. The sales really go high during that time for a lot of e-commerce websites. So you want to know how these things are changing, right? So they have found their use in weather forecasting, astronomy, I think in stock price prediction. But that in itself is a very difficult task to achieve, because you can model it as a time series. You can take a time series approach, but most of the times they are also dependent on a lot of other variables, which we will see while we do the coding part and the analysis part of it. right? So there are basically two types of models which we have. One is the univariate time series model and the multivariate time series model. So now what is a univariate time series model? Univariate time series model is something which like the data is only dependent on its own past values, right? It doesn't have anything else in the data set. It has just itself, and you have to pre-process the data set in such a way that y1 of t is dependent on y0 of t, and then y2 of t is dependent on y1 of t. So it's always dependent only on its past values. Multivariate time series is also another kind of time series where the data is not only dependent on its particular value, on its particular values, past values, it is also dependent on past values of other data series. So you might have temperature as well as population, and then you're trying to predict the population. So population might be dependent on the previous populations which you had, as well as the previous temperatures along those particular data, along those particular time orders. So that is how we look at multivariate time series. In this particular workshop, we are going to look at univariate time series, and but we would let you know what are the different approaches which you can use for evaluating multivariate time series. Right. So let's look at some of the properties of time series. So stationarity. Stationarity is a property of a time series where when you look at a particular time series, it might always be an increasing time series, or it might be a decreasing, or it might be a non-linear. But evaluating such things from a statistical point of view becomes much more difficult, right? Because you wouldn't know if you're saying that the particular data is increasing. Okay, fine. I model the I train the model in such a way that it was always forecast a value which is on a trending, which is on an increasing trend. But while doing so, you would also need to know that it might happen that the data is going through a dip after certain points of time. How do we manage that? So stationarity becomes a very important factor when you're looking at this, when you're looking at statistically evaluating these models. So stationarity says that whenever you have a time series, it should have its mean and covariance. It should have its mean and covariance constant over the change of time. So if you are given a time series model, right, you have to, if you want to do a statistical analysis on it, statistical models on it, and you want to build statistical models on it, you have to convert it into a stationary series if you're given a non-stationary series. So I would actually, we would go through that and how to convert those things. There are tests which you can perform on the data set which will let you know, or which would tell you that how to convert a particular data stationary series into a non-stationary a non-stationary series into a stationary series, right? The another property of a time series is seasonality. So seasonality is actually a property where you have a certain trend which is repeated after certain intervals of time, right? So you as you can see, like airline fares, I think also Black Friday sales and lots of such events, they occur after certain intervals of time, every few months, or every 15 days, or every 3 years, or something of that sort, right? That is called a seasonality. So it's a very important factor for that particular time series to and when you're building such models, to know what the seasonality is, and like after how many months, or after how many after how many intervals is that particular series repeating. Okay. And then we have something called as lag, which is the past values on which the current state actually depends on, right? So we are going to look at few of the statistical models. I'm not going to go much into the depth of the equations and what they are. I think I think you can have a look at them. There are lots of papers on them, but it's a very simple model. It doesn't have much of it. It doesn't have much of it as complex as other models you might have known in machine learning. So it's a like you have y hat of t, which is the predicted value, and it depends on the past values, which is y of t minus k, and you have something called as exogenous variables, which is the term E, and in loose terms, in actuality, that actually means the error which is there at each interval. So you have y1, and then you have error between y1 and y1 hat, and then you have y2 and y2 hat, and y3 and y3 hat. So these will be e1, e2, e3. That is how they take it. Error is not only the not error is one of the exogenous variables which you can have. You can have also average and rolling average, and lots of them. We are going to use, like for our experiments today in this workshop, we are going to use ARIMA models, which is autoregressive integrated moving average. So autoregressive, like this is basically a coagulation of two different methods. One is autoregression, which is what you can see as alpha 1 to alpha 1 y1 t plus alpha 2 y2 y t minus 1. So that is basically the autoregressive, because it is regressing on itself. And then you have e1, e2, e3 with multiplied with theta 1, which constitutes the moving average. And in ARIMA, the moving average is the white noise element in the data. In actuality, that is the error which you're going to have, right? So ARIMA model has three parameters, p, d, and q. The p, which is there, it corresponds to the autoregressive part. D is the differencing, and moving average of the system is q, right? Remember when I said the stationarity of a data? So when you convert a particular non-stationary time series into a stationary time series, you apply something called as differencing, which is what we have as D around here, right? All right. Yeah, no problem. How do we define them? How do we determine these values? We can use the autocorrelation plot, the partial autocorrelation plot, as well as the augmented Dickey-Fuller test. So these are certain tests which you can do to determine if the particular series is stationary or non-stationary. Autocorrelation is the data correlated with itself, with each and every interval points which are behind it. So you have y of t. How is it correlated with y of t minus 1, t minus 2, t minus 3, t minus 4? Partial autocorrelation is how is a y of t related with k intervals behind it. So that is how they define partial autocorrelation, and that's a very important test for determining the autoregression, basically the p-value, the autoregressive coefficient. Augmented Dickey-Fuller test is also a test which is used for determining the stationarity of the data. So I would actually show you during the implementation how we use them, right? So this constitutes the statistical model, and how like what are the different things which you need to do when you are trying to model these systems, and which you need to be aware of. What we need to do, we will see during the implementation part, right? So next, going forward, so now when we have such kind of models, or we have such kind of a problem where we not only need to know the current state of the data and the other dependent variables, but we need to know the previous values of that particular data, right? So we use RNN. So recurrent neural networks have come a long way, and they have found their use in natural language processing, in lots of other like I think BERT is one of the recent, I think, model which has come out, which is doing really well for machine translation and transformations. So looking at that, RNN is what we are going to use, is the model for recurrent neural network, is the model for designing such time series problems, for designing such time series models. We are gonna, but since RNN does not, and RNN suffers from vanishing gradient issue, we are going to use LSTMs on the hidden layer, right? So also along these lines, you have different architectures in deep learning. In RNN, you have something called as window based deep learning models. I think you also have time difference deep learning models also along these. So we are gonna review the window-based deep learning models, where we look at we look at the kth input as kth value from that particular output as the input to the net, right? So these models are very robust, and the basic thing which and a very important thing which is different from a time series model for a deep learning model is that the deep learning model doesn't have to know anything about the time series. It doesn't care if it is a stationary, if it has a seasonality, if it's mean, or if its covariance is varying over time, or if it's not varying over time. It just doesn't care, right? So what we have over here is what we will do right now in few minutes is that we are going to review these particular techniques, right? How statistical how does the statistical models perform as compared to the deep learning models, right? So I mean, I'm not going to go deeper into defining how LSTMs are. I think that should be that shouldn't be a part of this particular lecture. That might be because that's an extension. We are just going to use LSTMs, and I'm guessing a particular workshop on RNN and the LSTM and attention networks would actually define that, right? So in this particular workshop, we're going to see how we are going to use LSTMs for time series analysis. So okay, moving on. For forecasting the data. So we are basically evaluating the model. We use something called as root mean squared error. So now root mean squared error takes y hat, and it subtracts from the actual value of y which we have, and it takes a root of that. So so that's a very popular method which is used. I think for most regression problems they use root mean squared error, and we would see how that basically defines our model. We are also going to look at the plot visualizations which are there for like plot visualization is what I prefer when I want to do any of these when I want to evaluate the model, and they would definitely and they are very good at forecasting the value. So you can divide the data set into you can do an 80-20 split, but you cannot use the inbuilt, I think train test split is one of the libraries which is there. We cannot use that because that randomizes the data set. You cannot shuffle in this case because it is dependent on its previous values, and if you do that, I think you're gonna randomize the whole time series. So we are gonna split it into an 80-20 kind of a 80-20 or whatever percentage is good enough, and then we are gonna see how the model performs for that particular test data set, right? So what are the pros and cons? So statistical models are, I think, very quick, and I mean they have a very easy intuition to go to start with for implementing. So if someone asks you about like how do we go about this, like how can we forecast the values for the next few months, you would always use a statistical model because it's easier to understand, it's easier to like somewhat easier to implement, but it has a heavy component which is you have to know the statistical properties of the time series. Now at most of the times, I mean, it becomes a very difficult proposition because you might be differencing the time series and it is not becoming stationary at all. So it is non-stationary for lots of differencing. So you reach till d equal to 17, or for that matter of fact, you have to determine the autocorrelation coefficient, which is autoregression coefficient, and the moving average coefficient. So they are very difficult to to figure out, and you have to try them iteratively to get the optimal value, which is I think the AIC criterion. So that is one of the criterions which are used to determine which is the best model compared to different coefficients which we are feeding into the model. So you get the best coefficient of P and Q from there. And then there is also a particular issue with determining seasonality. If you do not know, if you do not exactly calculate the seasonality, or if you are a little off from it, your forecasts are either gonna dip or either gonna rise, and it would not follow that particular, or it would not be able to learn the system, learn the training data in a better way. So when you look at LSTM based models, they are in, from an intuition point of view, I mean, deep learning models are difficult, and I agree on that, and they are very robust in doing whatever they can do, and most of the times they have an overfitting and overfitting issue, where you overfit the whole data, so overfit the data into the testing, into the training set. So apart from that, I mean, LSTMs can be like your final model when you're doing a time series analysis. You do, the first step is to evaluate, and it's always better to look at the data, to visualize the data, do an EDA, which is, I think, a workshop which we are going to have in few weeks from now, and they would talk about this and how important that is. So statistical models in a way does that, and it's very, very important that you do that. LSTMs can be, or the deep learning based model is, can be your like last particular model which you want to, or the final model which you want to build. But in a way it doesn't have to be, because LSTM doesn't care about the statistical properties of the time series, and it just takes the particular time series, takes a window based, if I'm implementing a window based deep learning model, then it would take the kth value as its input and try to predict the and try to forecast or train the model accordingly. So again, that I'm not going to go deeper into how LSTMs are doing that. I think we are very, I'm guessing we are aware of that how LSTMs work, or how they go about solving this issue of taking, or they, how they accommodate previous outputs into the current um, output, right, into the current input. Sorry. As I said, there can be times where you have a multivariate time series, and I think there is an extension of ARIMA models, which is vector autoregressive model, and you can use that for building multivariate time series models, right? So that is basically how much the theory is behind all these things, right? So now we are going to go into the implementation of the time series models using Python. So we can think, go, okay, one second, we can go to the notebook first. So I have it on GitHub, but okay, I'll forward these links. I think these links will be available to you post this particular workshop. So once you have, I have taken a clone of this particular, okay, wait one second, I think okay, it's connected now. Do I need a GPU? Okay, I have, yeah. So I think, one second. So you load that. I think it should be there, and it should be inside my drive, and then time series, I think. Okay, cool. So I'm going to change the directory, the current directory of the lab, into that, and now we're going to import the libraries, right? So there are a few libraries which are required over here. You need pandas for reading the data set. You have matplotlib, and matplotlib is, I think it is one of the best data libraries I've used for plotting, and it has so many APIs which helps you analyze the data in such different ways you can never imagine. Uh, like I mean, you can have scatter plots with 3 dimensions and everything. So that's also possible nowadays. So then we have something like stats model, and which basically consists of these four of them. These basically consists of the ARIMA model, right? And there is something called as seasonal Arimax, which is what we will use to train seasonal data sets, and it requires an additional parameter called seasonality, right? And these are the LSTMs which are these are the deep learning libraries which you're going to use. We're going to use Keras for this particular workshop. You are free to use PyTorch or TensorFlow as it suits. But I mean, for this particular workshop, I could get it done with the Keras model, right? So for evaluating the performance, we have the mean squared error from the scale learned class, and we have few other things, right? So the first data set which we are going to use is the air quality data set. So let me visualize that also. I mean, let me bring that also. So that should be fine. So we load it. Oh, sorry. So we load it, and what one particular thing which you have to do while loading any particular time series data set is you need to apply a parse dates, because or else pandas is going to consider that as a string uh, column, and not going to identify that as a date. So it's a very important uh, it's a very important distinction which you need to, or it's a very important parameter which you need to provide while reading the CSV file. So when we do that, we have okay. So we have this, right? So date and time and nitrogen oxide which is generated at that particular day. So you have to. So this data is pretty old. I think 2004 on October the 3rd at around 6 o'clock they measured it around 166. Around 2000 in 2004 again 10:03 around 7 o'clock it was 103. So we have something like that, right? And we can also build we can build different kinds of time series model. We can build one which is taking the unit time, so 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, 10, I guess 11, 12. I mean that goes for the whole day. Or you can take one particular day, like let's say I take this particular day and I take the average, the mean of the nitrogen oxide, and see how like basically what we are going to do, what this particular notebook does is that it takes it tries to forecast the average value of that particular day, like how much is the nitrogen oxide. Nitrogen oxide is, I think, one of the greenhouse gases. Nitrogen oxide is how much of it is going to be generated on that particular day on an average, right? So that is what we have. So this is out. Okay, so now what we are going to do is we are going to do a basic plot, right? Basic plot of how and we would like to visualize how this particular and how the nitrogen oxide emission is. The unit of this particular gas is something which even I'm not sure of. I'm not sure what GT here means, but I'm guessing that is what would the unit of that particular gas would be. All right. So while we are going to plot the graph, we have to do something called as a date formatter, right? So date formatter is an important library of matplotlib. I think it's for matplotlib, right? Matplotlib, yeah, matplotlib, which parses the date in any particular format you want. So let's say I had it in a different format, right? 2004, it would have been in DDMMYY, right? Or MMDDYY. You needed to, I mean, MMDDYY is, I think, what is used most places, or it is DDMMYY, I'm not sure. But YMD is a particular format which is used mostly for databases, and and then that's where I think this data is coming from. So we are going to parse it in its base form as percentage y, percentage m, and percentage d. So date formatter which is also of matplotlib, helps you do that, right? So now what we are going to do is, if we display all the dates, so there are 391, I think, which is, wait 1 second, I think, yeah, yearly knocks is what it is. Yearly knocks will have 391 such points, right? So 391 on a particular x-axis would be 2 deaths. You would not be able to see, as well as you would not be able to infer anything out of it. So what we do is we take an interval of 30 days, which is like 1 month. Like every month you are taking an interval and you're saying, okay, 2003, 2012, 11, there was these many. 2004 110 is what it is. 2004 9, this is what it is, right? So you take an interval of like 30 days between each of them to find out whatever, and that is what you're gonna express on your x-axis, right? You can do a rotation of 45, you can do a rotation of 90. So this rotation is how much you want to rotate that particular value on the x-axis. So if you do a 90-degree, it would come directly below it. So these are certain things which you can do with matplotlib, and I think it has one of the best libraries for plotting graphs, right? So we have this, right? So now we are going to do something. As you can see, one thing which we can do right now is we can analyze the data, right? So it actually starts at a particular value, like maybe around 11th, and then post that it starts actually increasing and then decreases as it goes through that particular month. And again, when you get into the next month, it actually starts decreasing little bit, and then it reaches the minimum around that 5th, 6th, or 7th of the day of the month, or 10th of the month, and then it again starts rising. So you can see that there is a pattern, right? There's a pattern as to, like, the data actually starts during the starting of the month. Like the starting of the month, it is very low, but the nitrogen oxide emission actually increases gradually, and then again during the, like, when you have the last few days of the month, it actually dips, right? So that is something which you can see. So that is actually what we can say as a seasonality in the data, right? So you have a particular seasonality in the data, like how much is the data, like after how many intervals is the data varying. So we would look into that, like how much is it varying and how many times is it able to yeah, we can share the notebooks. We are I think we are going to share the notebooks. You okay, think I can. Okay, copy this link. Let me know if you guys can see the notebook. All right, so yeah, so we can see that the nitrogen oxide emission actually increases, and then it basically decreases through the end of the month, and that is what we mean by the seasonality in the data. And we are going to use one of that particular um, methodology to predict and forecast right now, as you can see. So, right, so now we are going to get into the building the statistical model for this, right? So we have the yearly emission, and we are going to index it at the date. So it is very important that you take this particular time series and you index at the date column. So date column is what we have here, and we are going to index it at that, right? Because if we don't do that, it is actually going to take the index as 1 2 3, and then we are not going to like you would not be able to forecast with the given month, basically, right? So what we are going to do is we are going to do an AD Fuller test, which is the augmented Dickey Fuller test, sorry. augmented decoupled test. So what that does is that gives the p-value for each of the uh, for the time series, right? So p-value hypothesis, I mean that's again that's a concept borrowed from statistical analysis. I'm not going to get deeper into that, but that has a critical value which is 0.05, and once you have a time series data which is when once you difference the data and you have a time series data which is below 0.05, that data corresponds to a stationary data, right? So when we just look at the data and we do not difference it, so we have this, we have the result, and which is what the data is, and we are not going to difference it. We just take the AD Fuller test. It is 0.35, which is much higher than 0.05. So what we are going to do is we are going to take the first differencing of that. So and we can do that using data.diff. I mean Panda series provides that particular API for you to take a difference. If you do diff of 3, I think it's going to take 3 differences. If you took diff of, if you do not provide anything, it will just difference it once, or you can do this also if you want to, but I would suggest that you do this if you want to. Anyway, and then you are going to drop the NA column from there. So because one of the first data will not be difference with any of the any previous value, so you're gonna basically have an NA over there, so you drop it, right? So now when you look at that particular data set, I mean when you look at the result of the AD Fuller test, right, with zero differencing it is 0.35, but with first differencing it is actually reduced to a very considerable level. So we can say that okay, first differencing is what we need, and now the first differencing data is what our stationary data is. Like at differencing of 1 is when we are going to have a stationary data. I am actually not very sure why the autocorrelation plot comes in this way. In my local it was coming much better, so I'm not very sure. So that I need to fix, and I would fix it with on the GitHub link, right? So you can look at the autocorrelation plot, and the autocorrelation plot basically on the first differentiation shows that all the values have a positive or below the zero line, right? That is not always preferable. You want the autocorrelation factor to be, or the autocorrelation plot to have equal or some data points below the below the zero line, because that's where you know that the data is stationary, right? Then you can do a first differencing of the, and then you consider the first differenced data, and you take the PACF. The PACF is a particular uh, library which takes the partial autocorrelation of the data set. So when you take that, it actually gives you the autoregressive term, but there are different ways of doing it, and there are different ways of determining the autoregressive term or the coefficient. Personally, the PACF plot doesn't, I mean it you can look, you can find lots of articles on it and how to evaluate it, but it's really difficult. So you can always get a upper limit on it, but you cannot get a definitive coefficient, right? So I mean we can look at the data and how the partial autocorrelation plot is and the autocorrelation plot is, but we are going to use an iterative method to look at the AIC values of each P and Q value which is generated, and then we are going to take the P and Q value which has the least AIC value. So right, so we initialize P values as between 0 to 7, and when we split the data size, so now we're going to take an 80-20s kind of a split. So you have 0.8 into data size and train and test, right? So then and actually this is going to take a long time to evaluate, so I'm actually going to skip. Although I'm on GPU, it actually took a lot of time to evaluate. And if you guys have any other, like I'm really open to suggestions on this, like how to do it in iteratively in a better way. But I had this particular idea and I did that. So what we do is we iterate through a given p value, and then we iterate through all the q's along it, and q is what your moving average is. So and the moving average is basically looked at through the plot ACF. So you can look at the plot ACF and determine that, but as I said, it's a very difficult proposition to do it, and I think you guys can already see how difficult it is to look at these data from a statistical point of view, and statistical models are difficult to build in that aspect. So when we look at this, right, so we look at this, so you look at all the PQ values, and you can see that the PQ value, which is the lowest, is at 3995, which is here. So P is 7 and Q is 6 would give you actually that particular value. So now what we do is we train the model with that particular, with those particular values, and I think this is gonna take time. Sorry guys, this just takes time. I'm not very sure why that does, but deep learning model, as you would see, is much faster than this. Yeah, if you guys have any questions, feel free to post it on the YouTube chat. Alright, it's done. So you can see that the AIC value is as what we expected, and you can also see that we had 7 autoregressive terms, right? These are the 7 autoregressive terms, and then you have the 6 moving average terms. And basically in in the space of mathematics, these autoregressive and moving average terms are the roots of that particular equation, and you identify them, I think, using different ways. I remember one particular way, but I'm not very sure if that is exactly what we use. So anyways, so basically these are the roots, the real root and the imaginary part of it, and this is what it is, right? So you can have a look at it from the summary if you do model train fit dot summary, and model train dot fit takes care of everything. So you can see that there is in ARIMA, which is the class, you have to provide the training data set, and you have something called as order. And the order is P, D and Q. D was 1 because first differencing gave us the least, basically gave us a P value which was very less, and 7 is what your autoregressive factor is, and P and Q, right, basically. So now what we're going to do is we're going to forecast these values. So forecasting is, I mean, again, this particular statistical model gives you an alpha coefficient, which gives you a confidence, which is like, okay, the data can be between a particular range to particular range, right? So it can be between like, I mean, this is the best fit which we have got, but this can vary between this particular these boundaries. So that is what we define using lower series and an upper series, and alpha 0.05 is what the standard is which we use, and that is what we are going to use for our data set also. So we give the like, now we need to give how many data points do you need to forecast it to. So now what we have trained is, we have trained this for the 80% of the data, which is, 1 second, I think it should be 390 or something, 270 I think. Let me just print it out. I think it might be easier than that. Oh, it again started. Sorry. Yeah, it's 312, and we had 391. So I think 312. I think it would be around 79 to 80 data points which we can forecast on. So that is what we will have in this particular, that is what we'll provide in the as the first argument, right? So now we use our, again, matplotlib to and whatever is the return values from them is the FC, SE and confidence. SE is I think SE gives you the series data. I'm not very sure about that. I need to check. FC series is what FC is what the forecasted values are. So we need to convert that into series, and that's what we do over here. And the confidence levels also, we convert it into lower series and an upper series, and then we plot it. And as you can see from the plot, this is the actual values are in orange and the forecasted values are in green, because you can see the green value does have a frequency, but it is not like, if you can look at this particular point, right, it is at this level, but sorry, I think we need to see from uh, yeah, yeah, sorry, because you can see it is actually somewhere close to a positive value, which is between 300 200 to 400, I'm guessing 300, and the actual value at that on that day, which is on the average, is somewhere around 175. So it's almost double. It's not doing that great, right? So remember, we looked at this particular graph, and then we said that there is a particular seasonal element in it. So a basic ARIMA model is not gonna accommodate that. So what we do is we add a, so we consider a seasonal Arimax model, which is this, and it takes a seasonal order, which is this, which is a seasonal coefficient. So we are going to use 12 as one of the values for this, and like the seasonal value. So we can say that okay, every 12 days is when it is changing. Again, determining this is only through the graph, and it can be right, it can be wrong. So I would suggest that again, iteratively, if you have to determine it, you have to have a particular way of determining all these values. So again, I am using another particular simplification which we have done while building this model, is while we have taken the same p and q value, which is for the ARIMA model, the same for the S ARIMA model also. Basically, it's called SARIMAX model. Yeah. So these p and q values are different from the p and q values which you provide for ARIMA model. In practice, they are almost the same, but again, evaluating them is something which is difficult, as I said, right? So we are going to take the same p and q value which is there for ARIMA, and we are going to say that okay, the seasonal autoregressive as well as seasonal moving average terms, which are these p and q, would be the same, right? So then when we build it, again, I'm not going to retrain it because it's going to take a lot of time, but I think I have to do it at least once, or else this model train won't be able to take it. Okay, so let's see, it might take some time to fit the data. And if you guys have any questions till now, so please feel free to post that on the live chat. I think meanwhile we can look at the different so this is where we are building a deep learning model, and you would see how, like, I'm not sure if it performs better, but it definitely gives you a better prediction. At least I'm not sure if it is overfitting. Actually, the other thing, mostly it is what I feel. Okay, anyways, I think it's going to take some time. So once we have that particular model trained with the seasonal data, you can see that the forecasted values still not better, but it is amplified than is little more amplified than the simple ARIMA model. So it is able to at least take into consideration the seasonality in the data series, and that is what we needed in this particular data set. So all in all, okay, fine, we are able to do something, right? So now we are going to move into the next part, which is building a deep learning model. So as I said, the deep learning model doesn't require you to know anything about this, about the any properties of a time series data. So you do not care if it's a uh, if it's stationary, if it's non-stationary, you just want to predict or you just want to forecast the values. The deep learning model would do that. The LSTM model would do that, right? So what we do first is that we use a scaler, which is min max scaler. You can use normal standard scaler also. I think that's choice. That's choice based, and I have always used min max scaler. So that's what we do, and we are going to do an 80-20 split because that's what we did for the statistical model, and that is what we are going to train the data on. So now the data series is only with the NOx values, and now you do not even want the dates in it. So what you're going to do is that you're going to split it in a way that you have the look back parameter, right? So the look back parameter is always one step behind, right? So one step behind, right? So that is the window based approach which I was talking to you about, which I was telling you about. So when you have the window based approach, you are basically uh, you take a look back, and you take the first value which is the current value, and you take the value which is just behind it. So that is how you build the LSTM. That's how you build the data series for this. Once you have after you have scaled it, so you have yk as the output, and then you have the input for that as yk minus 1, given that the LSTM also has the inputs from the previous step. So this is something which is a window based approach, and that is what we have built in which that is what we are going to use. So the default value of that is 1, and although I provided it, I think you can provide 2 or 3, and you can make it more robust. Sorry. So after that, an important transformation which you need to do is you need to convert this particular train x or test x or train y or test y into train x and test x into three-dimensional matrix. So you have the train x, which is what we need to reshape, and we are reshaping it into a three-dimensional matrix. So you take the train x dot shape of 0 and the shape of 1, and then you make the last column as basically the last dimension as 1 in our case, right? So then you use so now we are going to define the LSTM model. We are going to use a single layered LSTM, not a stacked LSTM. You can build a stacked LSTM, but again that depends on how robust you want to make the whole model as, and that is how you want to train, and that is how you want to look at it, right? So I'm going to take I'm going to take a single layered LSTM, not stacked LSTM, and we are going to have 4 of those neurons in there. And then after we have the LSTM, we have a dense layer, which is what is going to pack all the outputs from the LSTM and reduce its particular dimension into a single dimension array. And then you're going to compile, and you're going to calculate loss as a mean squared error. Mean squared error is the I think it is the loss which is used for most regression problems, and since this is a regression, not a classification problem, so you wouldn't be using softmax, and you're going to use an Adams optimizer, right? Then we go ahead and fit the training and the testing, the train x and the train y data, the training data set basically, and we take a look at epochs of 20. You can reduce the epochs if you want to, and we are not gonna do a batch standardization for this because it is not required. Oh yeah, it's transformed. Great. So you can look at the plot. So this is how the plot is. I think this would run much faster, as you can see. So then you have the batch size as 1, and we can make it verbose as 1, or I think if you make it as 1, I think it's not going to print at loss at each epoch, right? So once we do that, You can see that the loss is decreasing, but I think it doesn't decrease after, yeah, just in case I had the box. I think we can do a regularization and L1 and L2 regularization to limit the, or basically early stopping, to stop as soon as it does. Anyway, so once the model is trained, you go ahead and use the model.predict to get the train predicted data, the test predicted data, and then use inverse transform them, because we had to transform them, we have to now go ahead and take an inverse transform to get the actual value which we needed. And when you look at the RMSE score, the train score is 154.44. The test score is actually even lower than that. That can't be a possibility. I think it is mostly overfitting. But as you can see, there are certain regularization which you can do in this particular layer, and you would get a more satisfactory result. Anyway, so this particular score which you get, uh, that doesn't imply the percentage of error. That is just how much is your in the mean squared error is, but then you need to divide this by the total min max value which you have. So you have around 600 to 800, so 600 to 800, and I think you have to take a square of that, and then when you do a division by that, you would be able to see what is the error percentage in this. So 154 102.61 would come to somewhere around 99%. I think not even that, not that much, but it would come somewhere close to 80 at least on that scale. So, or maybe 90, I'm not sure, I didn't calculate that, but feel free to go ahead and calculate that. And then we are going to use the train predict plot and the test predict plot, and when we do a plot, as you seriously, oh, so you can see that you can see how the data is right now. You have the training data which is in orange, but the testing data, as you can see, it is very 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 close. Actually, it's almost, at times it is similar. Like, look at this particular point, it is almost similar, right? And it is able to follow the pattern in which the data is being generated. And here we have predicted the air quality of at each and every day using a deep learning model, right? So we have been able to take not only nothing else, just the nitrogen oxide data, and we have been able to build a time series data set after that, from that, and then we have been able to train the deep learning model to get this particular prediction out of it. And you can see that it's very very close, and this has been predicted, I think, 80 days in advance. So 79 to, like, that's close to like 2.5 months, right? So that's a pretty good way of predicting something, but I think you can go much farther than that, right? If you want to add on to this particular notebook, feel free. So that is my GitHub account. Feel free to go ahead and check it out, and take a stab at this. And I think this is a very famous data set which you can use for any of the research, or at least of building like trying out new models or new architectures on a time series model, right? So now we are going to move into the next model which we have, which is the COVID-19. So this is something which I stumbled upon like few weeks back, and I think me and one of my friend from Penn State, and we have been doing some research on this particular data set, and we would definitely like to show you what we were able to achieve. So this particular data set doesn't only take care, I think I should share this also, right? So this particular data set is, this particular notebook doesn't only look at building a time series data set, because that is one of the things which we need to do, but it also analyzes how the data is varying, right? So let's go ahead and get started, I guess. I think, okay, yeah, it's not there. and change the directory. Now, one thing which I found odd in Google Colab was in my local, I was using the Plotly library, which is a graph objects for plotting geopandas, basically world maps and everything. Uh, in my local, it had 4.6.0, but Google Colab didn't, so I had to restart. I think I have to restart my kernel after this. Okay. Okay, I don't need to. Very good. So these are certain comments which I have written. You can have a look at that. I think what we have done is we have used matplotlib and cbound for visualizing the data, and we have tackled that these particular project in building a time series model, which is one is the statistical model and the other one is a deep learning LSTM based model. And we have also looked as an extension of this. I mean, this is something which I'm continuing to do. So if you guys, any of you guys feel that you can contribute to this particular field or this particular research, please feel free to take this notebook and do it, because this is something which I feel is gonna result or is gonna definitely benefit or extend the research or make more people aware of what is how this how COVID has spread across the world and how it has and what are the different things which actually affect it, right? And like you might have wondered, right? It's like, is there a possibility that this can happen or this can become a seasonal thing, right? This COVID 19 or the number of cases actually peaked during the flu season in US, right? So it actually peaked during the Feb and the March month basically. Would it do it again next year? Does is it very highly correlated with certain parameters which are related to the weather, which are related to the population in that area? And like we are going to explore those things in this particular in this particular workshop, I mean in this particular notebook, right? So again, so we have similar libraries which we have used for the previous data set. But in addition, we have something like Plotly. So now, if you guys have worked with GeoPandas or plotting of graphical data with respect to world maps and all that, and Choropleth, if you guys have heard of that, then you might be aware of this. But if you guys haven't, so these are the libraries which are used to plot GeoJSON data. So you have countries, you have the world map, and once you have the world map, you want to mark certain regions within them as this or this many cases, or that is what this particular region is and what is the percentage of that is, right? So I would actually show you what the Choropleth graphs are. So that is an extra thing which we have used. Apart from that, I think we have used cbound to plot the correlation matrix, which we will come to in a while. So using that, I think you can get you can actually download the data set from Kaggle. I think it is into its week 5, so you would get recent data which is almost till today, I guess, but I have only taken a stab last week, so you have till 14th April, which is what we have. So when we have this and what we think, okay, I think we can print COVID data. So you can see that this particular data set has an ID, and then you have a country which is there and the date column with the number of cases and on that particular day and the number of fatalities. Fatalities is the number of deaths on that day in that particular region. But for this particular notebook, we have only used the number of cases which are there, right? So now how do we consider, right? So every day you have certain number of confirmed cases. That is what is reflected at this particular column, right? So what we are going to do is we are going to take the maximum, and now we are going to build it only. Now we are going to build it for the whole. What do I say? You're going to group and region it, grouping it by every country. So we are going to look at how like the number of cases for each and every country, like the maximum number of cases, right? So the maximum number of cases would only come when you consider the when you group it by the country and region, and you consider this confirmed cases particular column and take the max out of it. So this is what this particular line of code does, right? So then you load the world countries.json. So world countries.json, okay, let me see if I can actually show you guys that. So this is something which I've not built. You can take it from the GitHub repository, which is this, which is for Folium. It's another library which is very famous, I think, for plotting data. So what it does is it takes a type and a feature, and in the feature you have a property like name of the country and the geometry, and then in the geometry you have polygon. So polygon is again it's a shape which is used while plotting these graphical models of world maps, and that's a shape basically, and that is derived from the latitude and longitude of that area. So you can see the coordinates column actually gives you that, right? So we are going to use this to get the countries, basically the JSON of that. And then since okay, now I don't think we can see the extent to which the confirmed cases have arisen, but I think it's not going to be 17. I mean, as much as it is, I think it will be around 1 lakh or something. So sorry, 100,000 or something of that. So many countries have crossed that limit. So what we can do is that we are gonna convert this confirmed cases into confirmed cases log scale. So because you cannot have 35,000, because the plot would not give you any particular inference out of it, because you have so many number of cases in one region, and then you have so less number of cases in another region, right? So that is not going to give you a lot of inference, right? So what we are going to do is we are going to convert basically not the same column, we are going to add a new column which is confirmed cases log scale, and we're going to take the log of that. And since we have excluded the countries which have zero, basically confirmed cases zero, we are never going to have a division by zero on the log scale. Okay, I didn't. Okay, now this is the particular code for which you can generate a chloroplex graph. So when I run this, okay, this is why I did this plotly update. If you don't do it, I think it will not work on Google Colab. So when you have this, okay, so GeoJSON is the argument which takes the JSON of the countries. So you have the countries, and then in Z I have given the particular column which I want to print. Okay, and on the text, which is, so I have actually basically so what I have done is I have gone ahead and transformed the hover. So when you hover over any particular region, you can see certain text. So if you look at China, the actual value is 67,803. If you look at Iran, it is 74,877. If you look at US, it is 20,300. Sorry, 203,020. I'm sorry. Turkey is also high, Italy is also high. So what this text column does is it takes the confirmed cases which you have over here, and it's gonna print that particular, whenever you hover over the particular area, it's gonna show you a particularly basically a custom hover text. That is how it is. Feature ID key is a very important factor, because it is going to look at the GeoJSON, and it is going to look at which is the particular country or region I should be looking at, right? Or which is the particular, and how should I map the JSON into this particular data set which we have. So the only way we can do that is with the country and region, right? You have country and region, you have country and region. I think you have the properties.name over here. So this is how, right? And that is the reason why we did this for United States, because it was US in the JSON data, right? So that is how we are able to visualize. So now if you look at this visualized data, right, you can see that this particular area is being affected the most, right? So this particular belt, if I may say. So this is where the most number of cases are. As you go little, I mean, there are cases in Brazil also, but if you go into Africa and other places which are in the southern hemisphere. The southern hemisphere, I think, would be somewhere around this line, which is where the equator is. So it doesn't have that many number of cases, right? So this is the plot which we have for the confirmed cases, and this is what we call as a choropleth graph. I think there are other arguments which you can add to make it from a flat map to a globe. You can do that, right? So now what we are going to do is we are going to look at the data from every day. So what we have done is we have taken the country, region, the date, and the confirmed cases, and then we have taken for this is now we are going to look at the world, right? So how many number of cases are there in the world every day, and that is what we are going to forecast. So what we do is we take the country, region, date, and the confirmed cases and group by date, and we take the sum, right? The sum of the confirmed cases every day. So when we do that, we actually do this, okay, 1 second, and then we are able to see, as you can see, that the confirmed cases have actually been increasing till 14th. I think after 14th it has started becoming a little stable. I have not checked the news in a while. I need to I think they were saying that it is supposed to peak during this particular week, and news does say that it has peaked, but I'm not sure when it is going to become stable. So that is something which I guess we need to develop some time series model to or forecasting model to determine that, right? So we have confirmed cases which is every day, and the new cases which are coming every day. So you can see that the new cases have actually decreased. So I think that is why they meant, that is what they meant by stabilizing. So the number of cases which are coming every day is supposed to decrease. So you can see that it actually started from 0, then it actually dipped around the 8th of February, and then suddenly it rose to close to 10,000 15,000. This is the date. And then again, if you look at 11th, it was actually again peaking. So it actually decreases and then it peaks. At least it did that for the first 2 months, Feb and March. April, I think it was beyond us to get anywhere close, but I think you can see that it again peaked during the 9th, which is what it is. So I'm not sure how that works. I think I mean, that is something which is into deeper inference of the model would be able to tell you about it, right? So now we do a Dickey Fuller test. So now this is something which we have done, right? We have visualized the data, we know something about the data. Now what we are going to do is we are going to build the models, right? So we are going to take this and we are going to see the result, which is 0.9983, which is much higher than 0.05. So we take the differencing, and in this case what we have is the second differencing which is there. So now there are only 84 data points, not as opposed to 391 which we had for the previous one, for the previous notebook. So given this, you can see that the second order differencing actually becomes much stable. So like you do not have an increasing, like this is an increasing time series data, this is also an increasing, but in this you can see that it actually is rotating around a mean, right? And if you do a Dickey Fuller test, which is this, you would be able to see. Actually, we should be doing that. Let me do that real quick. Oh, sorry. Sorry, this has to be data dot. Okay, in first differencing itself, it has actually decreased a lot. So I think we can consider that as 1. Need to check that. Yeah. So I think we can consider the D, which is the differencing factor, as 1. But I think I've used 2 for some reason. Anyways, need to check that, right? Now we plot the autocorrelation, the partial autocorrelation, the autocorrelation plot again, just to look at the data, how it is partially autocorrelated or autocorrelated. So partially autocorrelated data, you can actually look at. This is a better graph to look at it. The number of data points after which the data actually becomes negative. So if you look at this, it is actually 1, 2, 3, 4, 4 or something like that, right? And then this also becomes negative after 1 itself. Then again this is becoming negative after 1, this becomes negative to 0, so something around those sorts. So that is how you look at the partial autocorrelation plot. The autocorrelation plot is also on similar lines, which defines your moving average. So now we do an 80-20 split. So 84 data points, we do an 80-20 split, so we get somewhere close to 68 and 16. So 16 is basically 2 weeks. So 2 weeks before we should be able to predict the data, right? Predict the number of cases. So this is where it is. And now there are I had done the iteration before, so what we got is that the p value with 1 and the q value at 0, basically 0 moving average, becomes an autoregressive model. It actually gives me the least AIC value, which is 1026. And when I plot along with that, you can see that this is the actual value which is going, and this is the forecasted value which is over here, which is in green. So it's still showing that it's an increasing curve, and this is the confidence level, that which means that the data can be between 2 into 2 10 power 6 to 1.5 10 power 6, which is actually a very high gap to consider. But this is the thing with ARIMA model. This is the statistical model actual output. So now we build the LSTM based model, which is this, right? So when we look at the LSTM model, we do not take any diff. We again do an 80-20 split, which is 16 7 17, and we have a look back parameter, and in this case we are going to use a look back of 1. I think 1 or 2 is what gave me the best values. I think you can look at 1 also, right? And train x and test x, right? So this is how we have reshaped the data, and now we are going to look at the LSTM model. So in this case, I have taken an LSTM of size 8, which is the hidden layer size, and when we train it, I think you can see that it has started decreasing. So once we do the root mean square analysis, it shows 278. So 278 is a test score, which is higher than the train score, which is good, right? The test score should be higher than the train score. So test score is higher. So now this 278 989, this is in percentage with the number of values you're getting. So this is 2 into 10 power 6. So I think close to 90% is what I'm guessing. 85 to 90% of error. Like 15 to 10, like 10 to 15% of error is what is there right now. So now what we do is we look at the plot, and if you look at the plot, thank God it is not overfitting exactly with the test data. It is actually going, and it is actually giving you an approximation of 1.5 or 1.6 into 10 power 6, which is what he was giving. And it is actually, and it's also able to follow the particular curve, and it is going, and it is able to go till that particular point. So imagine like 14 days before, you would be able to know if, given the current data, is there going to be an increase in the number of cases, or is there going to be a decrease in the number of cases. And I think I'm planning to do a similar model, but not for the confirmed cases daily, but the new cases which are coming daily, because that would be more interesting to know, and a better inference, I'd have to say, for deriving these data points. So this is what the research is. This is what I have done till now, and I think I'm going to use the vector autoregressive and create a multivariate time series also along these lines. Also use a stacked LSTM just to see how that behaves, right? I would also look at the new cases which are coming every day as another prediction problem, which will be for this COVID 19, right? So, again, feel free to contribute because, again, the GitHub link is public. I think you can go ahead and download or take a stab at it. Feel free to do so. Currently, this is what I have done right now. And then the next part of this particular experiment, which I have done till now, is how does the data vary with the temperature as well as the world population. So both of them are available online, and they are available only till 4th of April. I think they are. I think if you take the current correct. I think if you take a recent pull out of that particular day, if you take a look at the recent data set, I think it should have the latest data for every date. So what we do is we take again the data.csv, we look at, so the first, which is the temperature, you can see that it has actually the latitude and longitude column, which is what it had earlier, and it also has a day from 1st Jan, which is another particular date. So now in this particular case, you cannot feed into the model. If you want to feed the date, you cannot feed like this, right? So you have to take how much is it from the 1st of Jan, like how many day differences are you taking. So that is another transformation which you can do for the time series model or for the data set which has dates. So how do you accommodate the date into the training phase, right? If you look at the data from 1st Jan, and that is what it is. Temperature is in Fahrenheit, right? So that is the data set with the temperature. So now if you look at the data, so what I have done is every day I have taken the mean. So the mean of the data, the mean of the temperature between the 22nd of Jan to 4th of April. That is how we have taken right now. So when we take the mean and then we do this, we actually look at the graph. So now if you look at the graph carefully, right, a temperature which is around 45 to 50, 45 to 50 is where the most number of cases are, right? Okay, Poland is one exception, Germany is another. So 40 to 50, let's say 40 to 50, right? 40 to 50 is where the maximum number of cases are occurred. So does that correspond to a seasonal, because this was the flu season which was going around in this particular climate? Was that why people caught this? Was that why the number of cases higher? Um, okay, that is one particular case which you can look at. And then if you look at these particular countries, which is China and US, they have a very high population. So does it mean that when the southern hemisphere, basically the other countries on the other latitude, have a temperate climate between 45 to 50, 45 to 48 to 50, would they also experience a surge in the number of cases? So that those are certain points which you can derive, or which you can think of while looking at such graphs, right? So actually, let me see. Okay, actually, I think you guys can remember. I think, or just wait 1 second. Let me go there and show that also. Yeah, the number of cases highest in this belt. So this belt is, when I'm saying, I think it corresponds a lot with the latitude also. So we'll see that, right? So now we take the population data set also, and when we look at the population, we actually transform that, and we merged both the data sets, which is having the temperature as well as the population. So that is what this piece of code is doing. Also, population is very high between certain regions, so we take the log, because or else it will not be able to scale up to whatever the data which we are trying to show. So this is going to take, I think, a little bit of time to calculate the population. So I merge the data set. Sorry, if you guys have any doubts. So it is merged. Now we are going to take the dates and all the required columns, and we're going to drop them. So because we do not know the province and the country and province and day from 1st Jan, because we have transformed the date into, which is this, into the, wait 1 second, we transform the date yeah, which is here, date of year, day of year. So we are not going to take the this particular uh, temperature sorry, this particular day from 1st Jan. We are going to take the date which is of that particular year, like in that particular year what was the date, like, and then we take like 94 days is what we have right now, right? So okay, so we have done that. So now we label and code the country and region. We convert the date column, which is here. So you can see the confirmed cases log, the population is also converted to a log scale, and then you have the date and the log and the latitude, longitude and everything. We do a min max scalar, we look at the data, and we have only taken, we have not taken all the data, we do not need the ID. We just need the country, region, date, confirmed cases log, wind speed just in case, plus precipitation, fog, sorry, precipitation and fog, and temperature, population, latitude. So once we look at that, we take the correlate. I think my notebook just refreshed. Would I be able to do this? Okay, I can do that. Okay, I do a min max scalar, and then I do this, and when I look at the Seaborn plot, you can see that the confirmed case log okay, I think, okay, confirmed cases is highly correlated with the date. So it shows that there is a autocorrelation with the number of with the date, basically, and the number of days are basically from 22nd Jan it has always kept increasing. So there is basically a correlation around those lines. There is a high correlation with the population, which you can see 0.29, and also with the latitude. So latitude, I think that we can see from this particular graph itself that on this particular belt, when I said a belt, that is with this particular value or at this particular latitude, it has a very high correlation, and that is why it is 0.17, and then it has a very high correlation with population. So I think there is another school of thought where we can say that population is actually affecting the number of cases, because more the number of people, social distancing doesn't happen, etc., etc. So this is what we have done till now. I mean, that is how much it has been progress. I mean, other than that, I have dabbled into making other other networks around that, like how we can accommodate these particular data points. So next time I'm gonna like take the population, basically these particular columns, which is date, temperature. I have taken because I want to know how much it is actually affecting it, because if it's a temperate region, uh, if it's a temperate region thing and it's a seasonal thing, then it might happen that it keeps reoccurring. So that might be a thing. And I have taken population and latitude. So when we do that, and I have done few other things around that, but that's still incomplete. So this is what we have for the COVID-19 data set, right? So we have made some kind of progress along those lines. So if you guys feel that you guys can contribute to this particular notebook or to this particular research, feel free to reach out to me, or feel free to take a stab at that particular notebook from those GitHub links. And I think on the next email, we are going to send the GitHub links and the others and the other PPTs and things and the documents which we used here, right? So okay guys, this is the end of the session. If you guys have any question and answers, any questions for me, please post it on the YouTube channel. But apart from that, thank you for attending. That would be all.